Hello everyone, in this video we will cover the section 1.7. In this section we will learn linear independence. So an indexed set of vectors v1, v2, blah blah vp in Rn is said to be linearly independent if the vector equation written here has only the trivial solution. Actually we have here an homogeneous system by considering the coefficient matrix in this form, namely the vectors will be columns of the matrix A, v1, v2, blah blah vp. This is the coefficient matrix, and the right hand side of the system is zero vector, which means that we have an homogeneous system. And for this system, if we have only the trivial solution, namely the solution of the homogeneous system is just the zero vector, which is written like this one in matrix notation. So x is the zero vector, which represents the trivial solution, if you remember the preceding section. So if you have only this solution, so we say the vectors v1, v2, blah blah vp are linearly independent. The set v1 blah blah vp is said to be linearly dependent if there exist weights, scalars c1, c2, cp, not all zero, such that we have this relation. Okay, and this one is called, the equation 2 is called a linear dependence relation among v1, v2, blah blah vp, when the weights are not all zero. For example, in a set, let's say S, we have 5 vectors v1, v2, blah blah v5, and if we have a non-trivial solution for the system written as c1 times v1 plus c2 times v2, c3 v3, c4 v4, and c5 v5 is equal to 0. Okay, and after solving this system, for example, we found c1 is equal to 1, c3 is minus 1, and c5 4, and others are equal to 0. Okay, c2 and c4. So in this case the system becomes v1 minus v3 plus 5 times v5, 4 times v5. 4 times v5 is equal to 0. Okay, so we have a relation among the vectors v1, v3 and v5. Actually for all of them we have, but some of weights are equal to 0, you see, for example. And then we say this set is linearly dependent. This set is linearly dependent, okay, because we have non-trivial solution for the system. But if we find all of them as 0, namely c1, c2, blah blah, c5 are equal to 0, okay, this is the trivial solution of the system, so we say it is linearly independent. This set is linearly independent. For example, we have 3 vectors here, v1, v2 and v3. Determine whether the set v1, v2, v3 is linearly independent. If possible, find a linear dependence relation among the vectors if they are linearly dependent. Okay, namely we have to solve the system written as c1 v1 plus c2 v2 plus c3 v3 is equal to 0. And we must determine if there is a non-trivial solution of the equation on the previous slide, namely this one. Okay, So what is the augmented matrix of this system? The augmented matrix will be the coefficient matrix and the right hand side of the system, which is the zero vector, you know. So it is written as, what is the components of V1? 1, 2, 3, 1, 2, 3, and 4, 5, 6, 4, 5, 6, 2, 1, 0, 2, 1, 0. And the last column is the zero vector, since the right hand side is the zero vector for this vector equation written here. And we have to find the echelon form of the system. First we need to find the pivot position, which is 1 for the first row, which is the leftmost non-zero constant. And you can see here 1, 2, 3, 4, 5, 6, and 2, 1, 0. Okay. So after necessary row operations, you can do yourselves. Okay. This is your homework. If you cannot do, please ask me. So we obtain this echelon form. Okay, this is in echelon form. For the augmented matrix of the system, we have pivot position in the first row, and the second row has pivot position, which is -3, and we don't have any pivot position for the third row. And you know the variables x1 or c1, let's say c1, c1, c2, c3. Okay, we try to solve the vector equation c1 plus v1, c2 v2, and c3 v3 is equal to the zero vector. We have pivot positions for c1 and c2, but for c3 we don't have. So we say c1 and c2, namely x1 and x2, are basic variables, you know, and x3, namely c3, is free variable, namely c3, x3 can be any number. Each non-zero value of x3 determines a non-trivial solution of this vector equation. Therefore, v1, v2, and v3 are linearly dependent because we have non-trivial solutions. Let's say clearly, let's see clearly. From the second row, we obtain -3 times c2 minus 3 times c3 is equal to 0. From the first one, c1 plus 4c2 plus 2 times c3 is equal to 0. And c3 is free, therefore we consider this variable as a parameter. From the first equation, we obtain c2 in terms of the parameter. So we have minus t, okay, minus t, and c1 is obtained as c1 minus 4 times t plus 2 times t is equal to 0 from this one. So we have c1 is equal to 2 times t, okay, 2 times t. Therefore we have infinitely many non-trivial solution actually. If we write the solution vector x, so we have, instead of x1, namely c1, we write 2 times t. For c2 we have minus t, and the third one is the parameter, you know. And when we write any number for t, let's say for example 1, so we have 2 minus 1, 1. This is a solution for the vector equation written here. Writing the numbers into this equation, so we obtain a relation among the vectors v1, v2, and v3. 2 times v1 minus v2 plus v3 is a relation among the vectors you see. Therefore, the set contains the vectors containing the vectors v1, v2, v3 is linearly dependent. Linearly dependent. The set S containing the vectors v1, v2, v3 is linearly dependent. Linearly dependent. Okay, because we have non-trivial solutions, infinitely many non-trivial solutions for the system, and you see the answer also here. For example, if you write 5 for the parameter, so x1 will be 10, x2 will be minus 5, and you can obtain another relation among the vectors. Okay, this is one possible linear dependence relations among the vectors given in the example. So we suppose that you begin with a matrix A instead of a set of vectors, namely we are interested in columns of the matrix. So the matrix equation Ax is equal to 0 can be written as x1 times a1 plus x2 times a2 blah blah xn times an is equal to 0. Namely, this is equivalent to the vector equation, okay, by using the columns of the matrix A, and we know from the preceding sections the product of a matrix and a vector, okay, this is the addition of the multiplications of the components of the vector x and the columns of the matrix A you see here, and therefore we obtain a vector equation. So each linear dependence relation among the columns of A corresponds to a non-trivial solution of the homogeneous system. So the columns of matrix A are linearly independent if and only if the equation, the homogeneous system, has only the trivial solution. As we talk about the the solution of the vector equation. So if we say we have only trivial solution for the vector equation, it is also valid for the corresponding homogeneous system, for the matrix equation. Okay, if it has only the trivial solution, then the columns of the matrix is linearly independent, namely the set containing the columns of the matrix a1, a2, blah blah, an is linearly independent. Linearly independent. Okay, so this is very important concept. A set containing only one vector. Before seeing these important notes, let's solve an example about that. So we have a matrix A, which is 3 by 3, 0, 1, 5, 1, 2, 8, 4, minus 1, 0, 3 by 3 matrix. So determine whether the columns of the matrix A are linearly dependent or independent. Linearly dependent or independent. So the corresponding matrix equation will be A times X is equal to 0. Okay, we consider this matrix as a coefficient matrix for the homogeneous system written here. Since we have 3 by 3 matrix, so X will have 3 components, and the 0 vector will be in the 3-dimensional space. So the arithmetic matrix will be 0, 1, 5, 1, 2, 8, 4, minus 1, 0, and the last column is the 0 vector for the homogeneous system. After necessary row operations, you can do yourselves. We obtain 1, 0, 0, 2, 1, 0, minus 1, 4, 13, and the last column is the right hand side of the system. So from here we see clearly we have pivot position for the first row, we have pivot position for the second row, we have pivot position for the third row. Writing the equations separately from the echelon form, from the equivalent matrix. So we obtain 13 times x3 is equal to 0, x2 plus 4x3 is equal to 0, x1 plus 2x2 minus x3 is equal to 0. Okay, so from the first one, x3 will be 0. You see it clearly. When you write 0 for x3, from this one we get also 0 for x2, and therefore from the third linear equation we have x1 is equal to 0. So here you see we have only the trivial solution. We have only the trivial solution, the trivial solution, which means that the columns of A are linearly independent. So the columns of A, namely the set containing the columns of the matrix A, A1, A2, A3, is linearly independent, which means that we don't have any relation among the columns of the matrix A. Okay, we don't have any equation for the columns. When we write C1 V1 plus C1 A1, C1 A1 plus C2 A2 plus C3 A3 is equal to 0. So we say directly, because of this result, C1 is equal to C2 is equal to C3 is equal to the 0, number 0. Okay, therefore we say the columns of the matrix A are linearly independent, and a set containing only one vector, say V, is linearly independent if and only if V is not the 0 vector. So we have a set which contains a single vector, okay, vector V. So it is linearly independent if and only if V is not equal to the 0 vector. Okay, V is not the 0 vector, because if we want to find the corresponding vector equation for this set. So we have C times V is equal to 0 since we have a single vector. So to get a trivial solution, just trivial solution for the system, it is enough to accept that V is not the zero vector, because if V is not the zero vector, so to get the equality, C has to be the number 0, okay, the number 0. Therefore, the set containing one vector is linearly independent if the vector is a vector except the zero vector, okay. So this is because the vector equation x1 times v is equal to 0 has only the trivial solution when v is not equal to 0, that I said here. So the zero vector is linearly dependent because x1 times 0 is the zero vector is equal to the zero vector has many non-trivial solutions. You can write any real number for x1 because we have the zero vector here. So we obtain always 0, namely we have the equality for any number, for any value of x1. Therefore, the zero vector is linearly dependent if a set containing the zero vector, it contains the zero vector. So we say that it is linearly dependent. It is linearly dependent. So a set of two vectors, now we have two vectors in a set, is linearly dependent if at least one of the vectors is a multiple of the other. If at least one of the vectors is a multiple of the other. In order to say that the set containing two vectors, v1 and v2, okay, so is linearly dependent. Linearly dependent. If and only if v1 is a multiple of v2 or v2 is a multiple of v1, okay. If we have one of them, so we say it is linearly dependent because if you write the corresponding vector equation c1 v1 plus c2 v2 is equal to 0, so we have to get non-trivial solutions for the system. If we have one of them written here, for example, let's use this first one, v1 is equal to c times v2. So let's write this one. So we have c times c1 times v2 plus c2 times v2 is equal to 0, or from this one directly we can obtain a non-trivial solution because we have v1 minus c times v2 is equal to 0, and here c is not equal to 0, the number 0. This is the zero vector, and here you see we have a non-trivial solution because we have c1 is equal to 1 and c2 is equal to minus c, okay, minus c. So we have a non-trivial solution, which means that v1 and v2 are linearly dependent. We have a linear dependence relation among the vectors v1 and v2. So the set is linearly independent if and only if neither of the vectors is a multiple of the other, okay. When we have two vectors here, so we have to say, or for any number of vectors in a set, so we have to say that neither of the vectors is a multiple of the other for obtaining a linearly independent concept for the set, okay. This is the very important information. The set is linearly independent if and only if neither of the vectors is a multiple of the other. Okay, for example, we have a set containing some vectors v1, v2, v3, v4, for example, and we know v3 is 2 times v4, for example. v3 is a multiple of a vector in the set. So we have a non-trivial solution for the corresponding system, c1 times v1 plus c2 times v2 plus c3 times v3 plus c4 times v4. This is the corresponding vector equation for the set. And using this, we obtain v3 minus 2 v4 is 0, the 0 vector, which means that c1 and c2 are equal to 0, c3 is equal to 1, and c4 is equal to minus 2. Therefore, we have a non-trivial solution for the system because we have non-zero numbers for c3 and c4. So the set is linearly independent if and only if neither of the vectors is a multiple of the other. Multiple of the other. So characterization of linearly dependent sets: an index set S of two or more vectors is linearly dependent if and only if at least one of the vectors in S is a linear combination of the others. In fact, if S is linearly dependent and v1 is not zero vector, then some vj with j is bigger than 1 is a linear combination of the preceding vectors. So if you have a set of two or more vectors, so it is linearly dependent if and only if at least one of the vectors in this set is a linear combination of the others. Okay, namely we choose any vector from here, let's say v5. So v5 should be written as c1 times v1, c2 times v2, blah blah, c4 v4, c6 v6, and blah blah, cp vp. If we have a linear combination for some vector in this set, like this one, of the preceding vectors, so we say the given set is linearly dependent. Okay, linearly dependent. Linearly dependent. So Theorem 7 does not say that every vector in a linearly dependent set is a linear combination of the preceding vectors. The Theorem 7 says that we take a vector from the set. For example, again we have 5 vectors, v1, v2, v3, v4 and v5, and one of the vectors written here is a linear combination of the remaining vectors, which means that we don't have any information for the others. For example, we know v3 is a linear combination of the others. Let's write, for example, v1 minus v2 plus 2 times v3, v4, and 3 times v5. So it is a linear combination of the other vectors. except v3, and v3 is equal to this one, which means that the set is linearly dependent. This is the meaning of the theorem 7, because we have a non-trivial solution for the corresponding system C1 V1, C2 V2, C3 V3, C4 V4, and C5 V5 is equal to 0. Easily we can find non-trivial solutions for C1, C2, C3, C4, and C5. Writing this relation in this form, V1 minus V2, writing the vector V3 to the right hand side, so we have minus V3 plus 2 times V4 plus 3 times V5 is equal to 0. Therefore, we have a non-trivial solution because C1 is equal to 1, which is the coefficient of V1. C2 is minus 1. C3 is minus 1. C4 is 2. And C5 is 3. C5 is 3. So we have a relation for V3, but sometimes we may not obtain all of the vectors in a relation for the same set. For example, we can have V1 is equal to V4 plus V5. Again, we say S is linearly independent because we have a non-trivial solution using this one. V1 minus V4 plus V5 is equal to 0, which means that C1 is 1, C2 and C3 are equal to 0, C4 is minus 1, C5 is 1. So we have a relation for the vectors V1, V4 and V5, but we don't have any information for V2 and V3. We don't know whether V2 is a linear combination of the other vectors or V3 is a linear combination of the other vectors. Therefore, Theorem 7 does not say that every vector in a linearly independent set is a linear combination of the preceding vectors. If you have a linear combination for just one of them, like this one, it is enough to say that the set is linearly dependent. We don't need to find any information for the others. A vector in a linearly dependent set may fail to be a linear combination of the other vectors, like this one. Okay. For example, U and V are given here. Describe the set spanned by U and V and explain why a vector W is in span if and only if the set UV and W is linearly dependent. So at the beginning we understood that, if you remember, the set spanned by U and V is the linear combinations of the vectors U and V, and the vectors U and V are linearly independent because neither vector is a multiple of the other, and so they span a plane in R cube. Okay, you see U is not a multiple of V. We don't have any common number such that we can obtain the vector V by multiplying this vector U by this common number for the entries of the vector U. Okay, C times U is equal to V, and we cannot find such a number which is not equal to 0. Okay, therefore U is not a multiple of V, or we can say the same thing inversely, V is not a multiple of U. So U and V are linearly independent. The set containing U and V is linearly independent set. Directly we can say. So The set spanned by the vectors u and v forms a plane in three-dimensional coordinate system because we have three components for the given vectors. You see, if they are linearly independent or one of them is not a multiple of the other, so we say, if you remember, it span a plane in R cube. So span u and v is the x1 x2 plane with x3 is equal to 0. You see, we don't the third components are equal to 0, namely the vectors lie on the ground. If you remember, the vectors lie in the xy plane, okay, on the ground. If W is a linear combination of u and v, then the set containing these vectors u, v, and w is linearly dependent by Theorem 7. If you remember, if we have a linear combination for a vector in terms of the others, so by Theorem 7 we say W is the set is linearly dependent. Conversely, suppose that the set is linearly dependent, so by Theorem 7 some vector in this set is a linear combination of the preceding vectors. That vector must be W since v is not a multiple of u. V is not a multiple of u. Therefore, W is a linear combination of the vectors u and v. C1 times u plus C2 times v. Because u is not a multiple of v. So W is in the set spanned by the vectors u and v. It shows, so it is denoted in this figure, linearly dependent. V in span u and v. You see, u and v are on the ground, and W is a linear combination of u and v. Okay, you see. But in the second figure, the vectors are linearly independent because W is not a linear combination of u and v, because W is in different plane, in R cube, in different plane, which means that W is not equal to a linear combination of vectors, namely the addition of vectors C1 u1 and C2 v2. Okay, so this example generalizes to any set in R cube with u and v linearly independent. The set u, v, and w will be linearly dependent if and only if W is in the plane spanned by u and v. If u and v are not multiples each other. Okay. So another important theorem: if a set contains more vectors than there are entries in each vector, then the set is linearly dependent. That is, any set in Rn is linearly dependent if P is bigger than N. P is bigger than N. So let's see by writing an example. See the figure below for a matrix version of this theorem. Theorem says that if a set contains more vectors than there are entries in each vector, then the set is linearly dependent. That is, we have p vectors in the set, and it is linearly dependent if the number of vectors is bigger than the number of components of the vectors in Rn. Okay. So for example, here we have 5 vectors, namely 5 columns. If we consider the columns of the matrix as vectors, so P is equal to 5, and in each vector we have 3 components, therefore n is equal to 3, n is equal to 3, so P is bigger than n, so we say that the columns of the matrix written here are linearly dependent. The columns are linearly dependent because when we want to find the pivot positions, namely the echelon form of this matrix, for example, this is first pivot position, this one is the second pivot position for the second row, and this one the third pivot position, and these are equal to 0, you know. So for the first variable we have, this is basic variable, this one is the basic variable, this one is another basic variable. So we have 3 variables here. We have 5 unknowns for this matrix if we consider this matrix as a coefficient matrix for a system. So when we have 3 variables, directly we find a linear dependence relation, if you remember the first example or second example. Therefore, when we have columns bigger than the number of entries for each vector, so we have a linearly dependent set containing the columns of the matrix. Okay. Therefore, a set contains more vectors than there are entries in each vector, then the set is linearly dependent. And another important theorem, if a set S containing the vectors v1, v2, blah blah vp in Rn contains the 0 vector, then the set is linearly dependent because the 0 vector is linearly dependent always. Okay. By renumbering the vectors, you may suppose v1 is the 0 vector, then the equation 1 times v1 plus 0 times v2 blah blah 0 times vp is equal to 0 shows the set S is linearly dependent because we have non-trivial solution for the set S. C1 is equal to 1 and the others are equal to 0, so we have non-trivial solution, okay, for the given set. For example, we have 3 sets. S1 has the vectors 1, 7, 6, 1, 7, 6, 2, 0, 9, 3, 1, 5, 4, 1, 8. S2 contains the vectors 2, 3, 5, 0, 0, 0, 1, pi, e. And S3 contains the vectors 2, minus 2, 4, 6, 10, 3, minus 6, minus 9, 15. Okay. So which one is linearly independent, which one is linearly dependent? When we look at the first set. So we have 4 vectors. P is equal to 4. But for each vector, we have 3 components. 3 components. So P is bigger than n. So by theorem 7 or theorem 8, S1 is linearly dependent directly without solving the corresponding vector equation. Okay, we can directly say by using the theorems that we have seen here, S1 is linearly dependent. We can determine easily by using the theorems. For S2, we have the 0 vector, you see. So from the last theorem, we say that S2 is also linearly dependent. Linearly dependent. And for the last one, we have 2 vectors, namely it is enough to find one of them is a multiple of the other vector in the set. Let's look at the numbers. We should obtain a common number such that when we multiply the entries of the first one, we should obtain the second one. So to get 3, minus 2 should be multiplied by minus 3 over 2. So we obtain 3. Okay. So the common number will be minus 3 over 2. For the second one, let's do the same thing. 4 times minus 3 over 2. So we have minus 6. So we get the second entry. Similarly, by multiplying the others with the common number, minus 3 over 2, we get these ones, which means that if we say this is the vector v1, this is the vector v2, so v2 is equal to minus 3 over 2 v1, which means that v1 is a multiple of v2 or v2 is a multiple of v1. So the set 3 is also linearly independent. Linearly independent. Linearly dependent, sorry. Linearly dependent. Because v1 is a multiple of v2 or v2 is a multiple of v1, you see. We have non-trivial solution for the corresponding vector equation. Linearly dependent. Because we have c1 v1 plus c2 v2 is equal to 0. This is the corresponding vector equation, and we have to get a non-trivial solution in order to say that S3 is linearly dependent. So we have a non-trivial solution. So we can write C1 is 3 over 2, writing this one to the left hand side. Okay. And C2 is equal to 1. Okay. Okay. And that's it. Thank you very much for your listening.